So hi everybody, I'm Zdenek. I'm CTO at CODASIP. I hope that you have had a chance to visit the exhibition floor and that you've enjoyed first day of conference so far, because I did. But anyway, today's talk is going to be about the RISC-V IP and the customization or configuration that we do thanks to the studio. And by the end of this talk, I have two new announcements that I'd like to share with you. So let's start with the company introduction. So who we are? Well, we are CODASIP, so we are founding members of RISC-V Foundation. So we joined in 2015. We also introduced first RISC-V core at that year. And since then, we've developed the family we called as CODASIP Berkelium, as a tribute to Berkeley guys who actually came up with RISC-V, right? And we don't have just IPs, we have also EDA tools by which you can configure those IPs, and not only that, but you can also customize it. I know that the configuration and customizations are kind of similar things, but in the CODASIP world there is a difference, and I will talk about this later on. We are also active in the open source community, such as LLVM, LLDB, GNU tools, and so on. We are also members. We are also a member of several task groups, such as Trace Group or Pact SIMD Group or Compliance Group. So we're trying to push things forward to make RISC-V even better. But today's talk is about our approach to RISC-V. So what we have right now is we have a VK1, VK3, 5, and 7, which is like a starting point for you. You can use it as it is, without any customization configuration. There's just off-the-shelf IPs that you can just use. And if it fits, you're done, and it's all you need to do. But if there's something that you need to customize, you need to add more instructions, you can do, and you can do customization in every single BK that we offer right now. All of these cores are fully compliant with a specification, which means that whatever you configure, it's a RISC-V, and you should be able to run any code on these cores. Now, let me talk about configuration and customization and what it means in a CODASIP world. By configuration, we mean that we understand the fact that we have already written and developed certain instruction set extensions or instruction set things like integer set or multiplication and division set or compact instruction set. And we already have these ready for you, verified, and you can just use the tools and select, okay, I'm interested in I, I'm interested in M, and maybe floating point. And it's already there. You need to checkbox things, and then click on the button, and you obtain the IP that's according to your needs. The point is that it's already there, and this is the reason why we call it as a configuration. But not only that, we have like the standard ISA things such as IMC. We have also our own options such as jump prediction or caches or things like debug and trace, this kind of thing. So you need to just select whatever you need, click on the button, and you have it in a couple of minutes. Now this is a configuration, and the customization, it's something beyond that. It means that you have some secret sauce you would like to add into your core. It could be another instruction or bunch of instructions. It can be also some microarchitecture tweak or tweaks that you would like to have there. It can be also some, security, whatever things you would like to embed it into the core. So this is something that we call customization. So this is the main difference between those two in the CODASIP world. I have some slides on that with some kind of case studies where you can get with a configuration and what the customization brings you. So I will talk about this later on. Now, if you do customization, the questions that we usually have is, okay, so it's not that easy, because in the standard approach, what you need to do in the case of customization, if you're adding new instructions, you need to create a simulation models and verification models. You need to modify a C compiler in a way that it understands the new instructions and in a way that it's actually able to use it automatically in the best case. you need to enhance the debugger's tools to be able to disassemble these instructions or understand the instructions. And obviously, you need to write the RTL to have a real thing in the end of the day. And last but not least, you have to verify every single step, because usually you have separate teams that do such a thing. Now, it's quite challenging and time-consuming to doing in this kind of standard approach. So the automation is needed whenever it's possible. And this is the way where we came in and where we spent a lot of effort to make it as easy as possible. And this slide is like a CODASIP approach. We add as much automation as possible to every single step. So the thing is that you describe your extension, and again, it can be like instruction set extension, or it can be microarchitecture extension. You describe everything in a model, in a high-level description language that is able to capture these things. And then you click on the button and you obtain the SDK part that's aware of a new instruction. So you go to C compiler, an assembler, and these kind of tools that are aware of a new instruction that you just added. You have also ISS, fast ISS simulators, debuggers, profilers that, again, they are aware of extensions that you did. And then, obviously, you need to have the RTL in the end of the day, or cycle-accurate simulators that help you with the verification process and so on. So verification is also something that we generate for you. And then you can just use a script, and by the end of the day, or 2 days, you have a nice report saying everything is fine. The custom extensions works, and ready to go. Now, as you can see, it's a nice picture, but it's really a lot of work beyond that, and the tools has to be really smart to do the automation in the best way possible. We have a tool that we call Studio that does exactly this. So the Studio is here for a while. It's not a new one. It's been introduced in 2014, and since then it was adopted by major vendors and silicon proven. So we have designs that were done using a Studio. And the main thing is that, okay, so we try to target the automation process and make it as easy as possible. So we have created the architecture description language that's tuned for a processor design. And this is like the input to other tools, to generators, such as the RTL generator. So from this description, you can get the RTL in formal Verilog, system Verilog, or via GDL. You have SDK generator, so we use LLVM for a C compiler, so you get a customized LLVM compiler that's aware of your changes. You have also low-level tools, assembler, disassembler, linker, the everything you need to be able to program your code properly. And last but not least, you also get the UVM-based verification environment with all, we hope that we have everything you need there to be sure and to verify that there is no issue with the customization. There is nice IDE. It's Eclipse-based IDE. You have just one environment in which you do everything. So anybody who's familiar with Eclipse recognizes that there is a project. You have the main editor in which you do pretty much everything, and then some targets that in the end of the day generates the outputs, either Verilog or whatever. Now, the language itself, I have a dedicated slide on that. Just let you know that the language itself is quite powerful. So it's not tied to any particular architecture or any particular instruction. You can describe really simple ones, such as, bit manipulation, or you can also describe quite complex instructions that do, butterfly multiplications or some matrix multiplication. Or you can even connect some coprocessor or create a custom bus if you need that. And everything, again, is captured in single place in a CODAL. Now, this is another slide that describes what I just said. So, you have the input, which is the CODAL models. Then you put the input is, fed into a Studio, and by the end of the day, you have SDK, like for the programmers and software guys and firmware guys. And then you have HDK, which is hardware design or development kit with everything you need for synthesis and real design in the end. So let's talk about the CODAL language itself. So it's not tied to any architecture or any type of instructions or anything like this is quite generic, quite powerful. It's C-based language, so anyone who is familiar with C should be able to learn language quite quickly. And here is the example of that language. So you just need to describe the instruction in a text format, in the assembly format, and you need to define the opcodes and binary stuff. And more importantly, you have the semantics here that defines what actually is done, what the instruction does. In this case, it's just multiply and accumulate. This is a simple example. You can have more complex instructions that do more than that. Again, as I said, you can have instructions with multiple outputs, and still C compiler is able to use it automatically. You can always go down into assembly or intrinsics level and use it differently. But our goal is to make the programming model as easy as possible. The language itself is or the model, the description of a processor is split into two parts. The first part is called instruction accurate or functional model, if you will. And the purpose of that part is to focus just on the instruction set itself, and you give just enough information so the C compiler then is have everything that it needs. And then there is a second part, we call it as a cycle accurate part or implementation model, in which you add things such as timing or detailed description of low storage units or things that are things like forwarding or things like jump prediction and so. So this is captured in the cycle accurate part. Obviously, there are some code that's shared, such as opcodes, so you don't need to define those twice. But thanks to this separation, we are allowed to do verification nicely, and we also are able to have just one functional model and several implementations. So if you maybe you remember that we have like 5 implementations, so these 5 cycle accurate models, but the functional model is just one. So this is, again, a huge advantage of this language because it allows you to have a multiple implementation, and still the functional model is only one. Now here is the first use case I have here. It's a table that shows the project that we did with Microsemi. So they had a FIR filter. They wanted to use RISC-V, and so we just said, okay, let's do some experiments. So we took a base BK3 processor IP that we have, and we ran the code on that. And okay, we found out that we need like 1.7 million cycles to complete the computation, and the code size was like more than 200K bytes in total. And then, okay, the guys were, yeah, fine, this is something that we have already, but we need more power, more performance. So we say, okay, so let's try to add multiplication, because we saw in the profiling results that the multiplication is somehow needed in this application. So we added the cheaper one, the serial multiplier. And we ended up having 4,000K cycles. The code size is lower because we don't have to have that much emulations of the multiplication in the code anymore, because there is a single instruction that does it. So it was nice boost. It was like 4x boost. And the price in the gate is not that much. It's just 1.2x, so it was okay for them. But then they said, okay, let's do more. We would like to have more than that. So we have added parallel multiplier, which is a little bit bigger, as you can see here. But the performance is got to 1K cycles. So it speed up like more than 14x, which is good. And the guy said, okay, that's nice. The price is not that big. We can still afford that. But you guys need to do more than that. So this is the place where customization came in. In the CODASIP world, this is configuration, because this is something that we already have, and you just have a nice GUI in which you select what you would like to have. But that part is customization, because we sit down with them and okay, we defined like 20 or 30 instructions, DSP instructions with SIMD and these kind of hardware loops or zero overhead loops. And so we said, okay, let's try to do the experiment, and let's create this custom extension using CODAL. And so we did it, and we ended up having just 31K cycles in the end of the day. The code size is lower as well, because the newly added instructions were nicely designed in a way that we reduced a code size again. And if you look at the speed up we had, it's like more than 56x, which is huge if you compare the baseline. The size, well, yeah, we have added new instructions, so size is bigger. But yeah, the guy said, okay, we can live with that. And this is the stage where we ended experiments, because it was totally okay for them at this stage, because they met the performance requirements. At the same time, they met the area and the power requirements. So we just said, okay, that's it. So let's end here. So this gives you an idea where you can go with a configuration. And I mean, it's nothing wrong with that. It may be use case where it's completely fine, and you just need to pick and choose what we already have and verify. But there are cases in which you really enjoy, and maybe you really need customization, where you need to add your secret sauce or your custom extensions. And thanks to the studio, it was done quite quickly. It was done within several weeks, including designing new instructions. I mean, including this kind of designs per exploration. The end of the case study I have here is it shows the B extension that we did. B extension is something that's not ratified yet, but we try to keep up with working groups. So we have B already implemented in our course, and again, it's a configuration option. So even nowadays, you can just select, okay, I'd like to have B in BK5, for instance. And it's about 30 instructions. And thanks, given the fact that it's notified, so we consider it as a custom extension again. So it's not it's not ratified yet, unfortunately. In the case of a functional model, it took like 10 days to do it. It's about 900 lines of code. Here is an example of a gzip instruction. Again, nothing complex, as you can see. The most important part is here anyway, and of the function that does the gzip in the end. The point here is that thanks to the studio, everything was generated automatically, and you have something that you have SDK that you can use for software development in 10 days, which it's really impressive, I think. Then we moved to the implementation, and it took another 3 weeks to finish everything, including verification. So in a month, I would say you have a complete solution for bit manipulation instructions thanks to the studio. And there are some applications that really leverage every single instruction that's inside of B. It's not ratified, but we are okay with that, because thanks to the studio, it's quite easy to change it if the spec is changed. So I hope that it gives you some idea how important or how good the tool can be, and how it can help you with RISC-V related customization or extensions. Now, the verification is an important process as well. It's part of the studio. It's part of the methodology that we use. The bottom line here is that we use the functional model as a reference, as a spec, and we take the reference model out of that. And then we have a cycle-accurate model, which is implementation model, and we have the RTL out of that. And then there is a UVM test bench, a huge fun. And then we are able to generate test cases for you fully automatically based on the instruction set that you describe in the functional model. We have also a bunch of direct tests that we wrote for RISC-V. We also use other torch suites to make sure that the extension works correctly, and there is no bug in a microarchitecture, for instance. So thanks to the automation in the verification area as well, it reduces the time that's needed for verification and process in the end. So that brings me to the new releases, the new announcements that I'd like to share with you today. The first one is that we are releasing a new major release of Studio 8. It comes with nice features such as LLDB, which is LLVM-based debugger that uses Clang and other features from LLVM. We also moved to OpenOCD, so this is something that's really useful for on-chip debugging. We moved to LLVM7. We moved to the Oxygen release of the Eclipse. We have improved verification of RISC-V extensions. We have a new caches that are lower, more performance, and so on. So the new Studio brings a lot of new features that are tuned or targeted to RISC-V domain, and you can leverage every single one of them. And we used Studio 8 to build a new core, which is BK7, which is a Linux-capable core. It's a 64-bit core with everything you would expect from Linux-capable core. So it has branch prediction, it has MMU, 64-bit addressing, instruction dcache, acache, JTAG debug system, and thanks to the Studio, you can pick and choose whatever ISA extensions you want. Obviously, if you would like to run Linux, you have a certain set. But if you are not interested in Linux and if you would like to run something there, you can remove or reduce the number of extensions you have in the BK7 in the end. And yeah, to conclude this presentation, so sorry I'm a little bit over time. So the thing is that we offer the off-the-shelf processors, and there might be cases that's completely okay. Use what we have already. Just within a day, you have everything you need to start integration or start writing a process, start writing the software. Now, it may be the case that you would like to remove or add some already defined, already verified extensions, such as float, compact instructions, on-chip debugger, branch predictions, and so on. And again, it takes like a day to do it. And in a day, you have IP that consists of everything you need to start, integration and then software stuff. And if it's not enough, then you can do the customizations because we give you a tool, we give you a power to do it, thanks to the Studio. So then you can add your own secret sauce there, or you can ask us to do it if you want. But you can do it in your hand in the end. And you saw some examples of it, so I think the numbers talks for themselves. So should be okay.